Thank you very much. So, I'm actually going to talk about something we haven't done yet. I'm talking about actually a new research direction that we're focusing on and building up here in York. And I want to share with you why I find it so exciting and some of the history behind it and where I think it's going and why I think it's something really exciting to be about. And it all comes down to this kind of question. Can we heal people using electricity? So there's like a law. So if I'm a scientist and I'm talking about electricity and living things, the first picture I have to show is a picture of frog's legs. Can I get a sense of, in the room, are people familiar with experiments with frog's legs? Show of hands? Oh, right, I've got the most scientifically literate audience ever. Like, everyone knows about it. So this is going back to the work of Luigi Galvani in the 1780s, a very famous set of experiments looking at the effects of if you take two dissimilar metals and you touch the nerves of a frog's leg and a muscle, they'll twitch spontaneously. I was reading this, I was thinking, what set of circumstances do you end up with a set of dismembered frog's legs in your lab? And the story is that he was observing his wife prepare a frog's leg soup and the metal knife was cut. I mean, it sounds plausible, doesn't it? You've got to have a good reason. And there'd been a lot of, half a century prior of work prior to Galvani kind of looking at the effects of electricity. He wasn't the first. There are lots of experiments with kind of torpedo fish and other electric fish. But, this is the one that's really stuck out in our kind of collective memory and perhaps catalyzed a whole series of subsequent experiments over the next few hundred years. Now, where the biology ended up was this real understanding that we are these bioelectric beings. So this is a little cross-section of one of our cells. We've got a cell membrane, which is kind of the envelope around the outside of your cells, and most of us is kind of water, but within that water are ions, and ions are either atoms or molecules that have lost or gained an electron. So they have this kind of net charge, they're a little bit electrostatically charged. And cells are really interesting because they can regulate the flow of these ions across their membrane really well. They can kind of allow them to flow down the gradient, or they can even kind of actively pump them against that gradient. And whenever you've got a situation where you've got some charges over here separated by this kind of layer, and you've got a different concentration over there, there's a difference in that net charge, then you get a voltage. So all of our cells have this voltage across their membrane. And what's interesting is that also exists not just across the cells, but across some of the structures inside them, and across our tissues, and even across some whole organisms have these voltages present. So that's kind of where the biology's kind of taken us. But after Galvani's work and throughout the 1800s and 1900s, there was also this obsession with, this newfangled electricity, could we use it to make us better? Could we use it to heal people? And that led to things like this. So this is an electromedical therapy box. It's my electrical medical therapy box. I haven't told my partner that I bought it yet. Anyway, so inside, I've got a picture there just on the screen in case you can't see it, but inside there is this kind of black module and two connectors for a battery, and then a little very satisfying brass switch, and another couple of connectors for some electrodes. And in my box, I've got these kind of copper brass bars that are kind of wired on. I'm assuming you'd kind of hold them like this. Many different variants on this box were produced over many years. Many supplied with a large variety of electrodes for application to many areas of the body. And I'll leave that there. And what this box does, the problem is I didn't actually know what this box does. I bought it and I looked at it and there was some wires and a coil, I got some ideas. But I kind of wanted to be able to explain what it was doing. And I took it apart, or started taking it apart, and on the back there is, this is the top of the box, and then the circuitry, and quite frankly, it made me feel proud about my soldering skills. I was like, it's okay. It's not a particularly complicated circuit, but I realized that in order to understand it properly, I'd have to kind of tear it to bits, which I really didn't want to do. So I wondered, what if I plugged it in to see if it did anything? Genuinely, that was the point I remembered I was a scientist and had a lab. To that point, it hadn't occurred to me that I could just take it to the lab. So here we are in the lab. This is a nice modern bench power supply with 1.2 volts. Keep it nice and safe. And I'm connected it up to the terminals, and I've twisted this little arm here, and you can hear the buzzing. And if you zoom in, you can see that there's a little armature that's kind of vibrating backwards and forwards. And so what we've probably got here is a coil of wire that it's energizing, it's turning into an electromagnet, it's attracting that little armature to it, and as it pulls it across, it makes contact with the end, that gives us that kind of buzzing sound, and I'm assuming as it does that, it probably connects the circuit and discharges the electromagnet and flings back, and the whole process repeats over and over again. All right, so what's coming out of the electrodes at the other end? So I connected up my oscilloscope, and yeah, okay, we've got, oh my goodness, that's 50 volts. So yeah, so this little box can take 1.2 volts, about the power coming, or voltage coming out of a little AA battery, and turn it into a larger signal. I was feeling glad that I only chose 1.2 volts and nothing larger. So, and obviously it'd be very irresponsible and unsafe to see what was happening if you touched the electrode. So hypothetically, if one were to touch those electrodes at that kind of voltage, one would expect to feel a kind of light tingling sensation, the strength of which would depend on where you placed it on the body. And so this is what this box is doing. It's generating this kind of oscillating voltage. And it would have been supplied with a pamphlet a bit like this. So this is a couple of decades earlier, but a similar idea. This is the, I love the title of this. It's the Electropathic Guide prepared with particular reference to home practice containing hints on the care of the sick, the treatment of disease, and the use of electricity with full directions for treating over 100 diseases, which is quite hard to fit in the bibliography software. And it claims in the contents to cure a whole range of things, all the way from cold feet to cancer. So it's a real gamut of conditions that are kind of covered by this box. Now, needless to say that most of this is doesn't map on well to our current understanding of modern medicine, and a lot of it's been kind of dismissed as medical quackery. But what I found really interesting when I was researching this was actually this article from Professor Alison Marsh, who's a science historian, who actually really noted the fact that actually reputable scientists of the day didn't necessarily dismiss these systems out of hand. So this is Professor Benjamin Silliman, who was the first professor of science at Yale, who was endorsing one of these products, very similar kind of device. Now, that doesn't mean it's right. It doesn't mean it was working. Scientists can be wrong as well. But it shows you that the kind of contemporary thoughts of the day weren't immediately dismissive, that there was some interest in these devices and how they work. And what happened kind of subsequently and since is that we've kind of, these two areas, the biology and the medical devices, have kind of carried on being developed. Now, you can definitely go online still, onto certain online retailers, and buy magical boxes with electrodes that will claim to cure you and do all sorts of things. I would strongly recommend you don't spend your money that way. But what is interesting is that in the clinical space, there are certified medical devices that are available for clinicians to use, that are on the NHS, that use electrical therapy. A very wide range of conditions, but the example I'm just going to mention today is around bone growth stimulators. So in this example, if you had a fracture that wasn't healing, one of the treatment methodologies available, they have them at York Hospital, is to put the affected area inside a kind of metal, inside a cage, a kind of antenna, and to apply an oscillating electromagnetic field. There are variants that actually use direct electrodes, similar to the kind of box here. Now, I'm still very new to this area, and I am coming at this from a physics engineering background and reading a lot of medical literature. So far, my charitable interpretation of the literature is that the evidence supporting this treatment is mixed. And if it does do something, it's probably only doing it in a very tailored, specific use case. And these devices, these stimulators, are certainly not the kind of general all-purpose healing machines that a box like this claimed to be. But what I find fascinating is at the same time as that kind of therapeutic component and medical devices component has developed, so has our understanding of the biology and the role of electricity within living organisms. So on the right, we've got this picture. That's a flatworm. And if you look really closely, you'll see that this flatworm has two heads. So this is a series of work conducted by Michael Levin over at Tufts University in the US, which was looking at the role of bioelectrical signaling across an organism. And so this particular flatworm is loved by scientists because they regenerate really well. They can regrow limbs. So if you cut the tail off, it can just grow a new one, and it's fine. You can cut its head off, and it'll grow another head. But what they found was that if you interfere with the electrical signaling that's going across that organism, you can get it to do weird things, such as grow a second head. So it's got two heads or two tails and so on. Now, obviously, that's kind of quite bizarre and quite fascinating from a scientific perspective. But what it hints at is the role that this bioelectrical signaling plays in really fundamental behaviors, such as how organisms heal themselves, how wounds might regenerate. And what's fascinating is that that work is kind of carried on. So in other areas, in diseases such as cancer, you will see that actually the voltage across the cell in a cancer cell is markedly different to that of a normal cell. There are links in the kind of role that bioelectricity plays in all these different areas. If you cut yourself, you've kind of disrupted all those membranes and a bit of the kind of fluid leaks out. It generates its own voltage. Certain skin cells can sense that voltage and navigate along it towards the wound. So this is what I find really, really fascinating, that we've got mixed evidence with some medical devices that are being used in a clinical setting. We've got a lot of fundamental biology that hints at really fascinating kind of counterintuitive behaviors, that there's a lot of complexity there. And we've got this gap in between. And so this is the research area that I'm targeting. So this is the research group I'm building. It's called the Complex Interface Team. And our goal is to engineer, to make interfaces, or basically electronic circuits, that allow us to take some of those cell systems, to study them, to explore with biologists more of those effects, and start to think about how we could translate that into a maybe more nuanced and a more subtle approach in terms of engineering medical devices in the future. How can we take some of that knowledge that's being developed in the biology lab and apply it towards better ways of healing people? I find it really fascinating. It's quite scary because we don't know for certain yet. It doesn't work, and it involves a lot of mixing of disciplines, and it involves working with lots of different areas. One of the real strengths of York is that kind of collegiate nature. I can go across the lake to my colleagues in biology. We could start to build interesting interfaces and start to bring our teams together and come up with new ideas. The way I'm particularly interested in doing this is actually using plastics. So we're kind of taught that plastics don't conduct electricity. That's why we make kind of plug sockets out of them, because they're good insulators. Well, actually, you can engineer plastics so that they do slightly conduct electricity. Not as good as metals, but reasonably well. And so what these molecules on the left are particular kinds of plastics that, when mixed together, become slightly conductive. Now, what's fascinating about those is that they not only conduct electrons, which are the charge carriers going through all the wiring and the lights in our electronic circuits, they're also really sensitive to those ions I was talking about earlier that you find inside living organisms. So you've got actually a material here that acts as a really nice translation layer between the electronics world and the bioelectricity world. It kind of sits between those two areas. So in terms of our work, this is one of the material systems we're looking at working with. And I wanted to show you one final picture from the lab, because actually this is the electrotherapy box from earlier next to a microelectrode array. So this is a state-of-the-art piece of equipment that we have that allows us to very precisely interrogate cells and their electrical properties. And what I find fascinating is that these aren't the same box. The box on the left isn't claiming to be a healing device, but they essentially do the same thing. So on the right, we have a box that has two electrodes and generates these little pulses that you apply to a living organism. And on the left, and if you look right in the center of that little white square, there is a green square there, and that has about 3,000 electrodes on it, tiny electrodes, that allow us to apply similar kinds of pulses to individual cells and sense their response. And so this is the kind of tooling that we're working with and the kind of experiments we're doing. And I just find it fascinating. That's what 100 years of technological development can do. So that's where we are with it, and that's the start of this journey, and I hope I've kind of conveyed to you why it's fascinating, why there's this rich history there, and why there's a need to really explore that gap in the middle and understand how these interesting biological results can help us understand if we truly can heal people with electricity. Now, I'm also going to put an advert at the end. So if you're sitting there and you're interested in this research and you actually want to do some of this research, then I've got a PhD studentship that's closing at the end of this month. You can come and have a look at that and see if you want to apply it. We're looking at stem cells and bone generation and the effects of electricity on it. And I'll also be recruiting a technician and 2 research associates soon. So if any of that interests you and you want to be involved in that research, please find out more at complexinterface.com. Thank you very much.